Another characterization technique known as Fourier transform infrared spectroscopy. This content is used in lab number 5 of the spring 21 quarter for Materials Science 410, polystyrene synthesis by nitroxide-mediated controlled radical polymerization. So infrared spectroscopy is a technique where we use infrared photons to excite analyte, and by doing so we trigger molecular vibrations. So these infrared photons excite molecular vibrations in the analyte. We'll see here that the technique allows therefore for the detection of groups of atoms to allow for the molecular vibrations. So we'll be able to find functional groups that have these characteristic vibrations. By doing so and finding those signals in a specific region of the spectrum, you'll see that we can use IR to identify the type of polymer that is in the sample, or in organic chemistry, the type of small molecules that are present. This is owing to our identification of the functional groups that give the characteristic vibrations. So as such, infrared spectroscopy is quite useful in polymer chemistry since we're able to identify materials as well as handle and acquire the data very easily. In this lab and in many labs across the country, samples don't even have to be dissolved or processed, but simply placed on a spectral window to allow for the technique. So over here we have a graph showing wavelength of excitation energy. And you can see here that radio waves will trigger nuclear spin transitions, which is something we've seen when we discussed NMR. Earlier in the course, we discussed X-rays in and electrons out as a technique to identify metals in the form of X-ray photoelectron spectroscopy, and so that was formerly an ionization process. You can see here that the range goes from about 10 to the minus 6 all the way to 10 to the plus 5 or 6 for that X-ray technique. And we're going to find here that the infrared spectroscopy technique lies about midway there, around 10 to the power 1, or 10 to the power 0 in energy on a kilojoules per mole of photons. Okay, putting that all into wavelength using E equals hc over lambda, we can determine here the wavelength. So we're using excitation energy corresponding to a wavelength on the 1,000th of a centimeter is the wavelength of the radiation here. Okay, so as such, we've got to now be prepared to recognize and understand all sorts of molecular vibrations that may be triggered by this type of radiation. Shown here is, for example, the situation that we might have for a very simple CH2 group, something common to polymers. And so in here, the CH2 group, you can see here can be represented by the cartoons in our box. And you can see that all sorts of vibrations are possible, including symmetric, asymmetric, rocking, scissoring, wagging, and twisting. Many of these will be IR active, and those that aren't can be found by a complementary technique called Raman spectroscopy. So what are molecular vibrations? Well, we can model them according to two simple masses tethered by a bond, or a spring in this case. So we'll see here on the coming slide that physical models for how a spring oscillates with two different masses on either end can be brought into the theory here for the two atoms tethered by a bond. So we know that springs will naturally vibrate at some equilibrium bond length, and so we'll see that in many of our molecular systems. And of course, this equilibrium bond length can be represented by a more compressed state and a more stretched state. And a spring force would be needed to transition us from the equilibrium situation to those other options. So that is all to say that if a bond is stretched, a restoring force is needed to pull the two atoms together towards their equilibrium bond length. And if the bond is compressed instead, that restoring force pushes the atoms two atoms apart. And if the bond is stretched or compressed and then released, that we can consider the atoms in a vibrational mode. So Hooke's law is the physical model that we can use for this. Hooke's law speaks to the properties of a stretching bond and how they're similar to that of a spring tethered by those two masses. So the quantitative aspects here of Hooke's law is that it can relate the frequency of the oscillation of that spring related to a constant for that spring and what's called the reduced mass, mu, of the two tethered masses. So in other words, the two mass values have to come together mathematically to give us what's called the mass, the reduced mass, mu. We see the mathematics there for mu shown here, where the numerator is simply the product of those two masses, and the denominator is the sum of those two masses to give us mu here as our reduced mass. With mu in place, we can take that into the denominator here against the spring constant K for the molecular bond. We'll take the square root of that fraction and relate it to the inverse of 2 pi and a conversion constant to take us into appropriate units here for frequency. So molecular vibrations can only be found and considered IR active if there's a change in the dipole moment in the vibrational mode. So considering the vibrations we saw on the opening slide, let's rewind there. And considering a dipole, so considering that carbon is more electronegative, so the En value for carbon is greater than the En value for hydrogen, approximately 2.5 versus 2.1. We can see here that by stretching hydrogen bonds symmetrically, that the geometry of the system is going to allow for net change in dipole moment in this symmetric stretching case. We're going to see the same thing in, perhaps more obviously, in the asymmetric case, where momentarily one bond is further away, and that clearly is going to have implications on the dipole moment at that residue. Situations where we may have less obvious change in dipole moments can be represented here with the in-plane scissoring. But we'll see here that by bringing the two hydrogen atoms closer together, that the net dipole moment will be kind of emphasized geometrically towards the carbon in that case. Okay, and then in the case here for, as an example, out-of-plane twisting, you can see here that our dipole moment would be expected to be oscillating between two different options as the near and far options are considered there. Okay, so we need to recall how to understand a dipole moment based on electronegativity differences for the atoms in question, and then we need to consider how that might be modified according to our vibrational mode in question. Okay, so we need to be careful about symmetry. So completely symmetrical bonds tend to be IR inactive. So consider acetylene, for example, 1, 2, 3, H, H. And if we asked this half of the molecule to stretch that way and that half to stretch that way, the net dipole change, as we consider the elongated and shorter version, is a net zero change in the dipole moment, and this would be an IR inactive vibrational mode. It is to say it's allowed, but we won't be able to detect that vibrational mode using the IR technique, and something like Raman spectroscopy would be needed instead. Okay, so the two main vibrational modes that we want to consider are stretching and bending, and we'll see these in many polymer systems and functional groups. So a stretch is considered a change in the bond length, and this is typically found at higher frequency values. Bending is a change in the bond angle, as we saw a moment ago on that opening slide, And here, because it's easier to change a bond angle than to allow for longer bond distances, this is going to be found at lower frequency. So bending at lower frequency. There are much more complex types of bending possible, and some are called scissoring, rocking, wagging, twisting. We saw those a moment ago. Okay, so let's look at symmetric stretching of the water molecule. So recall here that our net dipole moment passes right through the mirror plane of the water molecule. And so by stretching the OH bonds further, we will be elongating the position here, moving hydrogens to a further spot. So we can expect a corresponding change in the dipole moments as a result there. So consider a vectorial approach here to understand how those two bond dipoles would add up to the net dipole, and consider a change in that dipole moment to register the whether or not this was IR active. Asymmetric stretching is probably more obvious here. So as we bring one hydrogen closer and one hydrogen further, clearly the net dipole is going to take on a new kind of angle versus where we started in the symmetric case. Bending and scissoring is also going to result in IR active modes, as the two lower electronegativity elements are going to be brought closer to the center point, and that's going to change our dipole moment between two options. Okay. Now, to help us predict the total number of fundamental vibrational modes that can be found, we have a couple of guidelines or rules to help us. So a nonlinear molecule, like water above, that's comprised with n atoms for this nonlinear molecule, can be predicted to have 3n minus 6 vibrational modes. So water, which of course has 3 atoms in it, so n equals 3. That's going to give us the 3 times 3 minus 6 for a total of 3 vibrational modes for this water molecule. And so those are shown above, as we just discussed. Okay, so here's a general IR spectrum, and here we see the intensity of the transmission plotted as the y-axis. Okay, so notice that 100 is the top of the graph. So if photons are passing perfectly through the material, then 100% of photons of, say, near 4,000 wave number are passing right through the material to the detector. If almost none are passing to the detector and instead triggering vibrational modes in the material, we can expect a very deep well in the spectrum on this transmission or transmittance. Transmittance. Y-axis. Okay, so percent transmittance. The x-axis here is wave number. Okay, so wave number in inverse centimeters to the minus 1. As you can see here, for the typical signals that we find in an IR spectrum, we find that most of these signals are found between roughly 500 and 4,000 wave number. And so using units that are in fact in reciprocal centimeters provides some nice numbers to use for reporting. And historically, this is the reasoning in using wave numbers versus frequency for the x-axis information. So as you might appreciate, wave number can of course be inverted to give a wavelength. And of course, with wavelength in place, this could be transformed into energy or even frequency mu. Okay, so considering more detail here on the x-axis, we'll see that we're going to consider a fingerprint region that typically is considered anywhere from about 1,400 wave number, sometimes as low as 1,100 wave number down. That is what we call the fingerprint region. Many very specific vibrational modes exist here for functional groups that are tied together with unique architectures. Above the fingerprint region, so certainly above 1400 wave number, we have more generic and more universal rules that can help identify functional groups. Okay, so like in the example shown here, we have a very strong absorption that's triggering almost all of the photons to be absorbed in the material and not transmitted. So we see a very deep well. And given the position of this peak, we know with great certainty that this is a carbonyl peak. Okay, and peaks, sort of inverse peaks, wells, very deep wells, shown more in the fingerprint region, are often harder to assign, but some are tabulated and can give pretty good estimates of the true vibrational mode present. Okay, so being more specific to that, here's a generic wave number versus percent transmittance graph again. No data is overlaid, but now we see some of the specifics here listed. So again, 1400 to 600 wave number is listed as our fingerprint region. This is where we're going to see very specific carbon-carbon stretching as single bonds, carbon-oxygen single bond stretching, and carbon-nitrogen bonds stretching. And of course, the dipole change must still be satisfied here. So we must observe a change in dipole moment in these architectures. Moving past this up to and outside of the fingerprint region, this is where we're going to find more universal rules, so regions get much tighter. And we can see that the carbon double bond region is roughly 1850 to 1600 wave numbers. And here's where we're going to find carbon-carbon double bonds, carbon-oxygen double bonds, carbon-nitrogen double bonds stretching. Moving up further, so we've seen singles, we've now seen double bonds. We're now going to see where triple bonds can be found stretching. And of course, we still must satisfy change in dipole moment for these. And so the example of acetylene a moment ago would not be found in the blue region, given that there would be hydrogens on either side of the carbon-carbon triple bond that we saw. If it is asymmetrically substituted, we can expect a carbon-carbon triple bond signal, and we would find that in the region of about 22 to 2300 wave number, more or less. Past that, getting to about 2800 wave number, all the way through to about 3500 wave number, we now see the XH region, where X equals nitrogen, oxygen, or carbon. So this is where we're going to see single bonds, but now with very different masses. The lightest element from the periodic table, hydrogen, bonded to carbon, oxygen, or nitrogen. The former, we had more symmetric weight, that is M1 and M2 from our reduced mass units, were closer to one another. And for these reasons, they're found at lower wave number. Another resource with more detail is shown here. So here you can see that we can put much more detail to this still and move past generic labels like double bonds and elaborate to the type of functional group containing those double bonds. So for example, carbonyls, shown in the middle there, can be found in a carboxylic acid residue, an anhydride residue, an acid chloride residue, an ester, an amide, an aldehyde ketone, and NH amides, or even, apologies, that's an NH feature. So all of those are the carbonyl C double bond O that we've just talked about there. So you can see very specific and sometimes overlapping ranges can be listed there. And in the case of carboxylic acids, those could be distinguished by esters by looking for the other piece of the acid group, which is, of course, C double bond tethered to an OH. So the OH, if also found, would help you put together that you have a carboxylic acid in your material. Okay, so again, turning to resources, that are tabulated, like those on this slide or other textbooks, can help with the assignments in a spectrum. We mentioned the wave number briefly. Let's consider some of the math. So, of course, we know that the energy is related to the photon with its Planck's constant and its frequency. Here, frequency must be in meters, and this would give energy in joules with Planck's constant as 6.626 times 10 to the minus 34 joule seconds. We can also use Planck's constants and the constant for speed of light in vacuum, and those come together as a numerator against a denominator for the wavelength for the same energy equation. So, once the wavelength is known, if we simply invert that, we have reverse meters, reciprocal meters, and of course that can be transformed into reciprocal centimeters to help us. So to give you a bit of a sense of scale, 1 inverse centimeter corresponds to roughly the 30,000 megahertz in frequency. So that is the energy associated with a photon having a wavelength corresponding to a wave number of 1 inverse centimeter would have 30,000 megahertz in frequency. Okay, so that would be F in the equation below. As far as energy, so a mole of those photons of wave number 1 inverse centimeter would be about 1/100th of a kilojoule. Okay, and then an electron volt, something we've seen before in XPS, we're into the 10,000ths of an electron volt. And as far as wavelength now, you can see how wavelength and wave number are related. And we're at about 10 million nanometers for the reciprocal centimeter. Okay, so how does the spectrometers work? We start with an infrared light source. So this is often a combination of 1 or more light bulbs emitting not only visible, but of course infrared radiation. A Fourier transform functions by splitting that beam into 2 parallel paths. So one is sent up to a mirror and back downward, and the other kind of half portion of the light source is hit onto another mirror and then reflects back downward. And these would otherwise be perfectly superimposable and have constructive interference. However, should a sample interact with one beam versus the other differently, there's an opportunity for interference that is non-constructive, where offsets in the pattern of the radiation would trigger destructive interference, and this interferogram is what we use to generate the ultimate spectrum via Fourier transform rendered here on a computer. Okay, so in short, light passes through the sample. You can see there's some complex mirrors and that can help us get the interferogram. Sample has to be thin and transparent to allow for this, and we can expect higher signal to noise when we can build up many scans and acquire numerous acquisition time for that. Okay, so what we use in labs and was becoming very common across the country is what's called attenuated total reflectance, or ATR. So an ATR accessory is often installed on FTIR spectrometers, and this works by bringing light in from a sample through a crystal which has high refractive index, and this is done at such an angle that there's total internal reflection along that material. Okay, so here if a sample, this could be polymer sample, for example, could be pressed up against a substrate, and our crystal is in the white material as you see listed there, and as our beam passes, we see total internal reflection as that beam reflects off the interface between sample and glass within the material that is our crystal. crystal is typically germanium or diamond, which has the appropriate refractive index to give us this high likelihood of total internal reflection. What's important is that at each beam bounce location, we have an opportunity to interact with the sample and have absorption of photons via vibrational modes that are triggered in that sample. So at each of these contact points of the beam with the sample, there's an evanescent wave that is created where the beam is interacting with that sample. This evanescent wave penetrates about 0.5 to 5 micrometers into the sample. And so we do acquire some depth information of the material, but we must have good intimate contact between the sample and that germanium or diamond window. If the sample is very granular and we're not getting a lot of contact points with the window, we stand a chance of losing the opportunity for signal detection or interaction of this evanescent wave at that internal reflection point, and we lose the opportunity to interrogate the sample. Okay, so it goes without saying that the absorption of the photons at this reflection point is what attenuates the reflected beam, and that's what we register ultimately on the detector for the spectrum. Okay, so here's an example spectrum for a very small molecule, fairly simple. So we can see here we've got a carboxylic acid functional group at one end. There is a chain of 6 carbons with internalized methylenes, CH2, 4 of those, and a terminal methyl. So that is hexanoic acid with one of the 6 carbons being on the carboxylic acid. Drawing of the molecule is here. And so the trained IR spectroscopist or material scientist knows to look for certain functional groups. And so we want to try to identify those in the carboxylic acid. So just by looking at that functional group, we're thinking OH bonds. We're also thinking carbonyl residues. And then as we turn to the rest of the molecule, we have CH2 groups. So we're looking for symmetric stretching and asymmetric stretching. And also bending modes can be considered. And in certain cases, the CH3 group can even be found with a symmetric or asymmetric stretch as well. Okay, so those features are all found in the above spectrum. We see the carbonyl stretch here at around 1711 wave number. We see the OH stretch at a large, wide range here, covering a span of about 2500 to almost 3500 wave number. That is very typical of OH stretches. And then imposed on top of that, we see sharper residues, which are typical of CH groups, and that's where we see symmetric and asymmetric stretching for CH2 and the CH3 group. So this IR spectrum has identified all the bonds present in the molecule, aside from carbon-carbon single bonds, which we would expect to find in the fingerprint region. So notice in this spectrum, those haven't been highlighted, but clearly some of the specific ones here and here are going to be unique to hexanoic acid and act as a fingerprinting bit of information. Okay, so with that, let's just clean up the slide so we can read some of the content that's speaking to many of the same points. Okay, so we touched on this earlier. As we go to higher wave number, this is going to be inverse with wave length, which is in the denominator of E equals hc over lambda, which means that E must be proportional with wave number. So in a sense, reading the x-axis is a little easier when we consider energy. So higher wave number, higher energy. Okay, that is also to say that since E goes with HF, or sometimes H nu, that we expect high frequency as well to the left on these IR spectrum. This is where we're going to see stronger bonds or lighter atoms present, like we have in the case of the OH and CH. The opposite can be said, of course, down towards the right, towards low wave number. We're going to see low frequency, low energy, and therefore weaker bonds that are easier to vibrationally stretch, as an example. Alternatively, we might see very heavy atoms tethered together by weak single bonds. Okay, so you can see here that a lot of series can be listed for us to prove some of these points. The carbon-carbon single bond has a weaker bond relative to the triple bond. Same masses are present in the form of carbon atoms, and so this lends to a nice series. And so the carbon-carbon single bond should be found at low wave number, low stretching energy, or low energy, bond energy, and that should be a low frequency oscillation. When we go to the very strong bonds that are in the form of a triple bond, these are going to oscillate with much higher frequency, as we see here at 2200 wave number, and the bond energy is going to correlate nicely there. So there we're going to see that at about 840 kilojoules. Okay. And the same series can be seen in like a heteroatom case where we put tether carbon and nitrogen together with single, double, and triple bonds, and the trends are validated there as well. As we go to stronger bonds, we're going to have higher frequency for those features in the IR spectrum. So in sum, frequency will decrease with the atomic mass increasing, or frequency will increase with the bond energy increasing. On that first point, we can compare carbon-hydrogen to carbon-carbon, ultimately to carbon-oxygen, and as the atomic mass increases from hydrogen to carbon to oxygen, you can see that the frequency is decreasing there. Okay, so in sum, we've seen that every organic compound can be thought to have a very unique IR spectrum. The IR spectrum can be matched to library, and many spectrometers have libraries built in, and that fingerprint region proves especially useful for that identification process, especially if a library is available. And so this low wave number range, 650 to about 1500 wave number, helps in that exercise. The rest of the IR spectrum gives valuable information about functional groups that may be present, and each type of bond has characteristic IR frequency, as we've seen tabulated in earlier slides. And the IR spectrum, to identify these functional groups present, can allow for the assignment of structure, especially when we combine it with other molecular information, such as that in NMR spectra, as we've done in our earlier lab. Okay, so we'll just consider these two polymers and think about what features we might look to identify to distinguish these two polymers from one another. So as we consider the molecular structure, looking only at what's on the slide now, consider pausing the video and thinking about what functional groups you would identify and which ones might give a unique signal in the IR to help you distinguish between pure polystyrene versus a very similar polymer that has copolymerized acrylonitrile present. What functional group might identify one polymer versus the other? Okay, so hopefully you've zoned in right here on the CN, the cyano group. So expanding on that, what that functional group is a carbon triple bonded to a nitrogen. Okay, and then we see that tethered to the polymer chain. And so this nitrile group is very unique and would not be found on pure polystyrene. and might be the feature to look for in the IR to show whether or not we have polystyrene co-acrylonitrile or simply polystyrene. So if we rewind, here you can see that that CN triple bond should be found with a stretching frequency around 2200 wave number in the IR. So if a signal is found here, we must be dealing with a nitrile-containing polymer, like styrene co-acrylonitrile polymer. So here's the two data sets. You can see that there's a lot in common, especially in the CH region. Those peaks just above 3000 are SP2CH stretches. Those below 3000 are SP3 bonded CHs that are stretching. You can see there are several signals there for both symmetric and asymmetric options. Those are also in common in the pure polystyrene. Other C double bonds associated with the aromatic groups in the pendant benzene groups are also going to be found with very similar features. And even the fingerprint is quite similar, making the identification here challenging. The unique feature that helped, that our idea was for the nitrile functional group, and here we predicted that this might give a unique signal around 2200 wave number, and here we see that screaming at us just above 2200 wave number on the x-axis there. Good. So in lab number 5 specifically, what we can consider is consider using the IR to speak to the purity of the material. So recall that styrene became polystyrene through our nitroxide-mediated radical polymerization, and there is the opportunity for an impure sample to be isolated. So if polystyrene were contaminated with leftover monomer, as you know, your conversion values may not be 100% from your earlier data, there's the opportunity for styrene to contaminate and contribute signal in the ultimate spectrum. So the combination of the two spectra on this slide could be found for a mixture of styrene with polystyrene. Consider what signals you might look for there to prove that, and ultimately this allows the student to comment on the purity of the isolated polystyrene. So to help with that, we identify a functional group here that has C double bond C, so looking for unique C double bond C features that are different than those that are in the aromatics, which are more like a C bond and a half C. And so the carbon-carbon double bond properly of the vinyl group in styrene monomer should be at higher wave number than that of the bond and a half in the benzene. Okay, so you can see here down in the double bond region that we mentioned earlier that in the monomer case, we're talking about unique signals in this region here corresponding to C double bond C stretch for the vinyl group. And most of that is absent in pure polystyrene. Okay, other signals that are shown here they correspond to an overtone set of signals due to the architecture of a singly bonded phenyl group pendant to this main chain. And so that pattern there is signature to a single bonded phenyl group on many atoms, and we see that somewhat present in the monomer as well. And so even though there is a tiny residue here, clearly that large spike there is represented the carbon-carbon double bond stretch in the IR. Further evidence to that can also be considered here in the SP2 CH stretching. So here we're looking for that same functional group. And here you see that those signals are not found, or sorry, are only found in the top monomer, superimposed in the polymer with the phenyl groups. But when we consider sp3 bonds, so this is carbon fully single bonded, we're talking about main chain features, so CH2s that are sp3 bonded instead, we're going to see these appear. And so those new signals there just below 3000, but still in the HX region, indicate the presence of the polymer main chain. So two features here to help us with that. So let's just clean up the slide so you can see all that a bit better. Absence of the double bond due to polymerization, and a new signal corresponding to the main chain sp3 CH stretches.